Today's presenters are Herb Schoeneman and Edmund Tang. You may remember them from their last webinar on package integrity testing. Edmund is a lab manager here at Westpak and has been with us for 9 years. He is also a professor at San Jose State University. Herb is the president and CEO of Westpak and has been here since the beginning. Edmund, take it away.
Thanks for that introduction, Greg. So today we're going to talk about dimensional weight pricing and what does it mean and how can we avoid large logistics costs, because with dimensional weight pricing, shippers will have to pay a lot more, and we're going to discuss, some details on how to try to avoid these shipments and cost, and pretty much how to calculate the cost that you're going to pay. But before that, let's get into just a little background of everything else, and let's just give dimensional weight a clear definition that everyone can relate to. So when you think about dimensional weight, it's simply the ratio between the weight and the volume of the shipper. So you have the weight typically measured in pounds, and then because we're in America with the English units, we either measure it in cubic inches or cubic feet. So cubic feet is highlighted in red because most carriers will charge in cubic feet, and that's why, again, it's bolded. And if you're in the rest of the world, you're probably thinking in metric, and that's kilograms per cubic meter.
Hi, this is Herb Schoeneman. I'm going to jump in here and answer a question that many people probably have, and that is, what in the world? Don't we already have dimensional weight shipping? And the answer is yes and no. Most carriers, and it was really started by what was then Federal Express, that ship via aircraft are familiar with dimensional weighting, because that's been the rule of the airways, if you will, for a long time. And the reason is the aircraft are limited in terms of the max weight they can carry, and obviously also limited in their cubic capacity. What came to our mind was that FedEx announced about 2 months ago that starting January 1st, 2015, they will also charge for ground shipment via dimensional weight. So they're going to apply the same basic formulas they do for aircraft shipment, have been using for aircraft shipment for a long time, to ground shipment. This may have some significant cost implications for some shippers. So we're going to investigate exactly what those might be, but also what you can do about them in the future. So this is a future event. This will be happening in a little over 6 months, but it's going to affect everybody, and it will likely affect more than just FedEx. The articles that I've read clearly indicate that UPS doesn't normally say anything about their policy until they actually implement it, but the chances are pretty good they'll do the same darn thing. Why wouldn't they? So this is a new shipping cost study, the methodology, if you will, for ground shipment, and it's going to be starting in about 6 months. Okay, Edmund, back to you.
Thanks, Herb. So when you think about dimensional weight, it's not always called dimensional weight, actually. Oftentimes, it's interchangeable with some other words. People oftentimes call them volumetric weight, dim weight, and cubic weight. But like I said, these 4 words, they're pretty much interchangeable. And dimensional weight, you kind of sort of think of, you've been calculating this all your life. Dimensional weight is another fancy way to say density, which is simply weight divided by volume. So when you determine dimensional weight, the most important thing that you want to take away here is that it ultimately determines the cost of transportation services. And it's based on, for your package, you're going to have the weight of the package, and you're going to have the volume, which is the dimensions of the package. And to get a volume of the package, you simply multiply its length times width times height, and you get the total volume of it. And you're going to put this package, or put this shipper into a vehicle, and the dimensional or the factors in the vehicle will be, 1, the maximum weight limit of the vehicle, and 2, the maximum volume limit of the vehicle, because once any of those 2 are exceeded, the weight or the limits of the vehicle is considered at max, and nothing else can go into the vehicle. So just simple calculations on density or cubic dimensional weight is when we determine the cubic volume of the package. So if you're thinking about units and pounds and inches, what you do is that you take your weight and you divide it by length times width times height. And to convert it to feet, you would actually just do the exact same thing, but you would divide it again by 1728, and that's just simply the inches to feet conversion. And you probably will want to do this because, like I said, most dimensional weight is calculated per cubic foot and not by cubic inches. Why is this important? Like Herb said, almost all carriers are now or soon to be calculating an allowable dimensional weight for the size and weight of the package you're shipping. And if the dimensional weight exceeds the actual weight of the package, you will be charged the dimensional weight. So let me just give you an example here. If you ship a 1 cubic foot box that weighs 3 pounds and the actual weight is again 3 pounds, but the minimum dimensional weight of the carrier is specified at 10 pounds, you're not going to be charged the 3-pound box. You will be charged a 10-pound box, which means that you have to spend significantly more money than what you would if it wasn't being charged as a dimensional weight package. And like I said, the result is a dramatic increase for revenue for carriers based on charging on dimensional weight. And this is also known as adjusted shipping charges. Adjusted shipping charges is pretty much being charged for something that's not actually there, but in order to make money when they ship out something, they're going to charge you, quote unquote, the right rate that they think that they deserve. And because there's a dramatic increase in revenue for carriers, what that means for shippers is that there's going to be a dramatic increase in cost for the shippers. And unfortunately, it's difficult to adapt and plan to because there's no have all to end all dimensional weight. Like for instance, I'm going to make my package this dimensional weight, 10 pounds per cubic foot, and I'm going to be good for truck, sea, and air, because that's definitely not the case. All carriers use different values, and different modes of transportation use different values. So that's why it's a little hard to plan for.
That's a very good point, Edmund. Consider that we've had some substantial experience, actually, with dimensional weight pricing from shipping via Air Express over a good number of years, 20 or 30 as a minimum. So we know what those are, and we know historically that in the days of the earlier type aircraft that were used, 707s, 727s, and similar, for those of you a little longer of tooth, you'll remember those. Well, they had much more limited spacing and power requirements, things like that. And so the number of 10 pounds per cubic foot wound up being a good rule of thumb, because when you cubed out one of those vehicles and you maxed them out in their weight capacity, that's about what you had. So that was the density that they were striving for, about 10 pounds per cubic foot. Now, since that time, larger aircraft, better spacing, bigger engines, you name it, have changed to the point where this standard density of air freight shipment is more in the neighborhood of 15 or 16 pounds per cubic foot, according to some sources. Okay. However, Edmund's point, which I want to emphasize, is that we don't know what the ground equivalent is going to be. So it changes with different states in the United States. It changes with different countries in terms of how much weight you can put on a single axle of a truck. But also there's dimensional weight to be applied to ocean-going shipments. So the ocean-going containers, the equivalent 40-foot container, for example, has a given cube. But we just don't know what the density specifications are going to be. Same thing with rail. Likely they'll be different, but pretty soon we'll be paying dimensional weight charges on all of these transportation modes, pretty sure. So, Edmund, why don't you continue?
Thanks for that, Herb. So what Herb just said was pretty much each vehicle, which is whether it's a truck, airplane, ship, or trains, it can only carry a maximum specified maximum weight and maximum volume. And the carrier's cost to ship a load will remain the same regardless of what is shipped. So whether they ship the airplane or a full airplane, it's going to cost the shipper the same, no matter what. Same thing with the truck. A half truck or a full truck is going to cost the shipper the same. So the carrier feels like their billable weight should be and will be either the actual weight or the dimensional weight of the cargo, because that's the only way that the carrier will ensure they're getting paid appropriately for the space on the packages that they take up on the vehicle. And like, you'll always get charged whichever is greater. So I know I gave you the example of the 3-pound box being charged at a 10-pound box here, but let's just say, for instance, your box isn't 10 pounds, it's 20 pounds in a cubic foot. You're actually going to be charged at 20 pounds as well. And what this is telling here is that carriers will always have the advantage, and people shipping out packages will always have the shorter end of the stick because they'll be charged either the minimum or the actual weight of the package. And you think about it, we've been shipping packages forever now, and one might ask, okay, why dimensional weight now? Why is it getting so popular? And a couple of reasons why is because, one, it's just a response to the rising fuel costs. When you think about rising fuel costs, you think about fossil fuels, and they're only going to dwindle, and they're not going to replenish themselves really. And with that, we have a supply and demand problem, and fuel cost is just going to rise, and they need to offset the cost of the expensive fuel cost with dimensional weight cost. And the second item is just the popularity of online shopping and automated systems. So you think of the Amazons and McMaster-Cars, not too much the eBays, but especially the Amazons. We all shop at Amazon. I shop at Amazon. And when I place an order, I wouldn't be surprised if my order gets shipped out within the next 3 or 4 hours from just placing the order. And the reason for that is because the Amazon system is highly automated, and what that means is that it's just, they sacrifice, speed for packaging efficiency here. They take your product and they drop it in the box, and they look at it and say, okay, we have X amount of void here. Let's stick some void fill here and be done with it. And they don't really look if your product is a stuffed animal or if it's a hard drive or if it's a laptop, really. It's more like, okay, there's 3 inches of space on top. Let's just make sure the space on top is filled and nothing's really rattling in the package, and we ship it out. And because of that, what happens is that with void fill, it's just very light and not dense, and when that happens, you actually clash with dimensional weight because you have a box that's usually relatively large, and the density of it, it's fairly small.
And that's a good point that had been brought out, is that the use, or in some people's opinion, the overuse or misuse of void fill may be a contributing factor to why carriers are demanding a dimensional weight via ground shipment. That may still very well be true. In order picking operations such as the ones that were mentioned, it would be very difficult to engineer a package system for each box going out the door. So these void fill techniques help us keep costs down in terms of the packaging cost, but they raise the logistics and distribution costs because of the inefficiency in the travel and the delivery process. Of even greater concern to us, however, are so-called engineered packages. So if you have a device that has a fairly large number of quantities to be shipped on a regular basis, where you physically engineer the package system. So you make sure it's got the right dimensions, you make sure it's got the right fragility, the right characteristics, that is the cheapest cost, that it performs correctly, all those kind of things. When you go about doing that, you use cost as one of the criteria, but never has cost been affected as much by density as it's going to be in the future. So what we're really saying is that density winds up being another of these required characteristics that you have to consider and design for when you are designing an engineered package system. So even though these McMaster-Cars and Amazon type shipments using void fill wind up being a concern and certainly a cost center, they've probably driven the FedExes of the world to this particular point. They're not the primary ones that we're really talking about. We're really looking here at engineered package systems, and we'll be talking extensively about that in the next couple of slides. Edmund, back to you.
Okay, next point is that Herb touched on this a little, and I'm just going to elaborate a little more, but there's no common or standard dimensional weight ratios, but there's definitely common dimensional weight ratios that if you don't know any better, you're going to say, okay, I want to have something around here just so you have a good starting point. So let's just say when their dimensional weight do get published, you're not completely out of the water here, and that's common IATA shipments, it's around 10.4 pounds per cubic foot. And then for common domestic shipments, it's 8.9 pounds per cubic foot. And you look at those two values, like Herb said, they both hover around 10 pounds per cubic foot. And if you don't know better, that's what you should definitely strive for. And it might not be 100% on the mark, but you might be a couple pounds off, but you'll definitely won't be in a bad position if your dimensional weight is around 10 pounds per cubic foot. And when you think about packages and products that are likely to be penalized, especially lighter packages and lighter products and things that are kind of sort of fluffy. You think of popcorn, you put a popcorn in a 1 cubic foot, no way is that popcorn going to hit 10 pounds. You're probably going to end up with a 3 or 4 pound box that will end up being charged 10 pounds. And same thing with styrofoam cups and just pillows that don't really get crushed, but then these packages and these products will definitely be penalized as not hitting the minimum dimensional weight that the carrier state. And for the products that you don't really have to worry about hitting the minimum dimensional weight, but you'll actually be charged the actual weight, are just heavily dense packages. When you think of equipment, machinery, raw materials, anything, a bowling ball, anything that's really, really dense, you will probably have no problems at all hitting that minimum dimensional weight. You'll be charged the actual weight.
It's important to look at the history of this whole thing too. We're looking at 10.4 pound per cubic foot as a common, what's referred to as IATA. IATA is the International Air Transit Association. And these are the folks that set rules and guidelines for shipping by aircraft. And then the common domestic shipment is a ground shipment. So if you took all the trucks on the road today and you somehow were able to say how much weight did you have on them and how much volume do you have total, you'd come up with somewhere in the neighborhood of about 9 pounds per cubic foot. Those of you who look at how much our roads get torn up, you know that an average is simply that, because there's going to be things on the very light side of that and on the very heavy side of that as well, and that's all determined by the result of this density number that Edmund has in this particular slide. So again, it's not the heavy things that are going to get penalized here, it's the light ones, because we're trying to get the proper density then, or FedEx is trying to get the proper density in all their shipments. Good luck. They'll probably do it. They're pretty determined folks. Edmund, back to you.
And if there's anything that you should take away from this, why it's important, it's just that companies should try to optimize their package system to be as close as possible to standard dimensional weights, because nobody likes to waste money, nobody likes to be charged for space not used, and avoid adjusted shipping costs. And it's just not in shipping, just in real life. Nobody likes to pay for something that they're not buying, actually. Okay. Next topic online is, how is dimensional weight measured? I know I gave you a little background on dimensional weight, talked a little about the history. Let's just go through some raw calculations. Actually, no, this is not the calculation slide, sorry. So if you're thinking about large carriers like FedEx and UPS, they have thousands, 10,000s, millions of packages being shipped. And with these large carriers, you wonder to yourself, okay, are people going to come out with tape measures, rulers, and scales and measure everything? No, everything's obviously going to be measured in an automated inline conveyor system. And with the conveyor system, you know that it's efficient, high-speed, accurate, and you could kind of sort of say, most importantly, no human interaction required. So on the next slide here, we have a diagram of some packages just going through the system. So it's an automated conveyor system, and the first thing that the package hits is a light curtain. And the light curtain will take the highest or the tallest dimension for the height. Secondly, it will take a laser tachometer, and with that, it'll pretty much measure how long it took for your package to cross that to measure the length. And lastly, it'll go through another laser to measure the width, and finally being measured by a scale. So if you look at this diagram, something that you'll notice is that all these boxes are nicely rectangular boxes. And pretty much when you calculate dimensional weight of a rectangular box, it's just really easy to do. It's a pure calculation, length times width times height. But on the next slide, we introduce some kind of oddball shaped packages. So let's just say you're shipping a drum or a cone or something, and because these laser systems are measuring the maximum length times width times height, your cone or your cylindrical pail right there becomes a rectangle. So it's not actually measuring actual volume, but rectangular volume, to say at least. And your second package here, let's just say you have a package, and then at the very end of the package, you change your mind and you want to stick something on top of it, and you want to ship it like that. And the system's not going to measure that as a separate little, you could say, knob on top. It's going to actually measure it as one big rectangular box, which will increase the volume dramatically. And for the last example here, when you ship something that's triangular shape, it's going to turn it into a rectangle. Like I said, length times width times height, maximum. And this is just telling you that when you ship something, you definitely want it to have it in a quote-unquote standard size, because that's pretty much the way you will be charged. And when you have a box that is really heavily dented or just really heavily smashed and it goes through the laser system, it's going to measure all the protrusions and all the just the loose packaging parts as the maximum dimensions. So that's something that you should definitely be careful about. Okay, so now let's go on to some calculations. Like give some background, give some history, give some definitions. But what's really important is just examples and how to actually calculate everything here. So for the first example, we have a minimum weight allowance for the carrier of 20 pounds per cubic foot. And we have a shipper size of 12 by 12 by 12. We conveniently have the shipper size of 12 by 12 by 12 because it calculates to the cubic foot conversion of 1. So for the first case here, we have a box that weighs 10 pounds. And the weight to volume ratio is 10 pounds per cubic foot. But what you notice about 10 pounds per cubic foot, it's under the 20-pound minimum allowance. And what you're going to be charged for is 20 pounds. The second case here is that you have the same size box, but it weighs 20 pounds. And 20 pounds equals the minimum, so you're actually just going to be charged 20 pounds. This is the best case scenario, actually, because you're not exceeding the minimum weight, and you're not really getting charged anything. And here's the last scenario, that you have a 12 by 12 by 12 box, but it weighs 25 pounds. And because 25 pounds weighs more than the minimum weight allowance of 20 pounds, you'll actually be charged for the 5 extra pounds, which is known as the actual weight of the shipper. But in the real world, nobody really ships a 12 by 12 by 12 box every single day. And when's the last time you shipped a 12 by 12 by 12 box? I don't remember the last time I shipped a 12 by 12 by 12 box. So let's give some real examples here of little boxes that are differently shaped, and also something with a minimum weight allowance that is more reasonable in the real world, which is 10 pounds per cubic foot. So with this example, our first shipper is 24 by 12 by 12. With a 24 by 12 by 12 shipper that weighs 30 pounds, you convert it, and that's equal to 2 cubic feet. Weight to volume ratio is 15 pounds per cubic foot. And because 15 pounds per cubic foot exceeds the 10 pounds per cubic foot minimum limit, you're going to be charged 15 pounds per cubic foot, which ends up being charged a 30-pound box. Second example here, we have an 18 by 18 by 18 box that weighs 20 pounds. When you do all the conversions, it ends up being 5.9 pounds per cubic foot. 5.9 pounds per cubic foot is less than 10 pounds per cubic foot, so you're going to be charged 10 pounds per cubic foot. So your charged weight will be 33.75 pounds. For the last example here, we have a box that is 10 by 10 by 10 that weighs 10 pounds. And when you do the weight to volume ratio, it ends up being 17.3 pounds per cubic foot. And 17.3 pounds per cubic foot is greater than the 10 pounds per cubic foot. So therefore, you're going to be charged actual weight, which is 10 pounds. Or the dimensional weight, actual weight, which is 17.3. But the charge weight of your box, since it's not 1 cubic foot, it's 10 pounds.
It's again important to remember that the density is what we're really looking for. So density is a weight divided by the cubic volume of your container system. As mentioned earlier, if you have an oddball shaped something other than a rectangle, you'll be charged the rectangular size of that particular structure rather than its actual size. So if you're shipping cylindrical containers, either large or small, that's the old proverbial sticking around peg in a square hole, because the distribution environment is definitely square, rectangular at least. So you'll be penalized for that, because any kind of odd-shaped structure is going to get a dimensional envelope put around it that is the equivalent of a rectangular envelope. So anything that you can do to make your product more cubic or rectangular will help in that regard. And believe me, I'm not trying to advocate for everything being square in the world. That's not the case. But guess what? FedEx and UPS and shippers in general will charge you more if they're not. And again, all goes back to density. So Edmund, take it away.
Thanks, Herb. So now that we've done some calculations, you're probably wondering, 10 pounds per cubic foot, that's a little hard to meet. And you're just wondering what you could do in the real world to actually try to, strive for these types of values. And we're going to leave you, or we're going to go through 3 pointers that you could do, as a company and you actually have control over to actually improve the dimensional weight of your product and package. So the first thing that you could do, or the first item that you could do, is just determine the product fragility of your unit. Too many times customers come to Westpak as a testing lab and they say, okay, test my package, but at the same time, I don't want my unit to ever see 50 Gs because that's fail. And then our common response to that is that, okay, 50 Gs, it fails because what breaks? And they say, oh, nothing breaks. It's just in our specification it says no 50 Gs. And then you kind of ask yourself, okay, because it doesn't break at 50 Gs, but you're still packaging for 50 Gs, what happens? Obviously, you're having an overpacked package, and because of that, your cube isn't as well, because you know that with overpacked package, you have additional foam, and foam will make your package system a lot less dense than it needs to be. The second item on the list is just to improve the product or improve the ruggedness of the product. So when you improve the ruggedness of the product, you assume that you've already done step 1 of determining product fragility. So you already know where your package breaks or your product breaks at. And with this step, you're willingly to do a little investigation and say, if I throw a couple more dollars into this product, if I make it a little more robust, how much materials can I save? How much will my cube improve here? And that's when you put when you want to improve your product. So anything from improving 50 Gs to 60 Gs and cutting off half an inch from each box on each side might give you a better cube. But that's something you need to calculate, which we'll go over later as well. And the last item that you're in direct control of is just changing cushioning materials. So different materials offer different deflections and protection characteristics at different thicknesses. And I'm just going to go over 2 very, very common materials in the industry. One is expanded polystyrene, which people know as styrofoam. And you think of styrofoam, it has a working percentage of 50%. And what this means is that if you have a 2-inch thick polystyrene, you could deflect 1 inch before it becomes hard and useless, and it actually will damage your product because it's so hard. And secondly, second type of material that I'll talk about is expanded polyethylene. Expanded polyethylene, it has a deflection rate or deflection percentage of around 70%. And because it deflects a lot more with the same 2-inch piece of polyethylene, you actually get to deflect 1.4 inches with the same 2-inch piece. So that's another way that you could cut down on the cubed.
Thanks, Edmund. This is probably the crux slide of our presentation here, because it tells you what to do about things. And I do have to say that it doesn't give you all the clues, because suppose you have a product that is not cushioned. How in the world do you manage, if you will, the density of your product package system if there's no cushion in there? Let's say you have a device, call it a medical device, and a tray, a thermoform tray, let's say, and typically the density of those things is pretty low. So but there's no cushion in them, at least for the most part. They're not an engineered system in the traditional sense. But there are things that you can do to that. But the net effect will be to improve the density. In addition, improving the density by optimizing the cushion. That's really what you're doing with this step 1 and 2 here, is optimizing the cushion system. After you determine product fragility, which is a very straightforward process. Many people think that's overly expensive or somehow black magic or something like that. Nothing could be further from the truth. It's very straightforward. But when you have the numbers, and by the numbers I mean you're able to quantify the ruggedness of your product, and you can do that. You have 2 choices. You can say, well, shucks, I need X amount of cushioning, or I need to strengthen the product, because the product and the package work together to resist the forces of the distribution environment, typically impacts and vibration, compression, and things like that. So if you, as Edmund mentioned, take the same amount of money out of the package, put it into the product, you're going to wind up with a smaller package system from a cube standpoint. You're going to optimize your shipping costs because you're going to be closer to or perhaps even over the dimensional weight limit, whatever that happens to be, and we really don't know what that is yet. Okay, but look at it this way. Here's how I like to say it. If you add value to the product by making it more rugged, that value stays with the product its entire life cycle. From the time it's put into service to the time it's actually taken out of service, and that might be, years, that can be months, years, or decades in some products, but it stays with the product. And so every time someone kicks it or drops it or things like that, obviously accidentally, that kind of ruggedness will make for better clients, better customer service, a lot happier clients, and guess where they're going to come back to when they need something like that in the future. So it makes a lot of sense to make the product as rugged as possible, not only to reduce the cost associated with packaging it and shipping it, but also just the customer goodwill that you're going to generate by making the product more rugged, more resistant to the kind of things that are going to happen, not just in distribution, but throughout its entire life cycle. So don't minimize this so-called product improvement function. I think it's very, very important. I think we should concentrate on it a lot more as a society, not just as a group of packaging people. It really makes a lot of sense. So we'll talk a little bit more about that in the future. But again, that's I think the key element of this whole presentation is don't minimize the effects, the positive effects of product improvement, product ruggedization, product improvement feedback, whatever you want to call it. It's a very important function. Edmund, back to you.
Thanks for that, Herb. Okay, so when we're doing the first step, which is determine the product fragility, what we're doing is that what we're testing towards is a product shock test per ASTM D33332, method B, in case any of you guys are curious and want to look at it ourselves and the specification. But what this test does is that it simulates a package being shipped into the distribution environment. Package being shipped meaning, human people and dropping the package, throwing a package, distribution environment, but it's all related to the package. And secondly, it's a margin test. What the margin test means is that we slowly take the package, or we slowly take the product to failure. So you'll start at a relatively low level, like 30 Gs or 40 Gs, and then you'll shock your unit in every single 6 orientations, which is top, bottom, front, back, and left and right, because once the package leaves your hands, you have no idea, you have no control over the way the package is going to be dropped. You can't tell the FedEx person or FedEx driver, okay, every time you drop this package, make sure it's on the base, because it doesn't work like that in the real world. And after you shock in every single orientation on one level, what you'll do is that you'll do an evaluation. Evaluations usually consist of, one, a cosmetic evaluation, just to make sure your unit is not aesthetically damaged, and secondly, a functional evaluation. So you'll take your unit and then you'll run it through a series of diagnostics to make sure nothing really adversely changed. And at the end of one level, if you would call it pass, this unit that you just shocked and a brand new unit should have no difference at all. And if that's the case, you would bump up your test to the next level. So let's just say you started at 40 Gs, next you would go to 50 Gs, and you'd do the exact same thing. And you would kind of sort of just wash, rinse, repeat this same method until two things happen. First thing that could happen, that usually happens, is that your product breaks. And when your product breaks, you know exactly where it breaks at. So if it breaks at 80 Gs, then you know that, okay, theoretically, I never want my product to see 80 Gs during the distribution environment. So you'll design your package for a 70 G package. And the second thing that might happen is that you'll actually max out the shock tester at maybe 140, 150 Gs. And if this is the case, what you know is that your package and your product is really, really robust. And that's really, really good because you need minimum foam on each side of your product. And like I said, it's a margin test, and you also determine exactly how and where to package your product. And let me just address this because some people might be wondering here, okay, this is method B, Edmund, so what happened to method A? Method A is actually a specification for bare product testing, so in-use environment testing. So once you take your laptop, once you take your cell phone out of its package and you have it in your hands and you could start dropping it on a concrete floor or the wood floor, then that would be method A. But because method A doesn't deal really with the cube and doesn't really deal with the package, we're not talking about method A here.
That's a really good point, Edmund. Many of you are familiar with at least the terminology damage boundary testing, which is really what this is. And it's a product test. It's not a package. It's a product test, and it's a product test to failure. Ultimately, that's what the standard encourages you to do. Anyway, many people take shortcuts with it because of the lack of product available for potentially destructive testing. But the important thing is that walking out of a damage boundary test, you have a lot of information about exactly where and how the product breaks. Over the past way too many years that I've been doing this kind of work, I've been absolutely amazed at what fails and how, and also what people do about it. There are many examples of relatively fragile products during initial testing, but if a designer is there or someone who has responsibility for it, increasing the ruggedness of a product substantially, some cases double, just results from another screw in the bracket or a bigger screw. So some relatively minor stuff can result in major increases in the ruggedness of the product, major decreases in the cost to pack it, and now major decreases in the cost to ship it. So don't discount this kind of stuff. And again, it's a margin test, as had been mentioned, and that simply means you take it to failure. So you know that in the case of a product that is extremely rugged, you know exactly how much headspace or margin, as it's called, that you have built into the product package system. And it's always a good idea to examine that. It's been the source of many a cost reduction study that I've had to utilize in my past lives at other firms, and it's come in very, very handy. Lots of war stories about that we don't have to get into now, but again, don't discount this product shock fragility analysis in terms of the really incredible cost savings and cost avoidance that can be engendered from these numbers. Edmund, back to you.
For those of you that are not familiar with a shock tester or shock testing, here's just a picture from our lab here of a shock tester. So what the shock tester does is that you mount your unit rigidly on the table. So right here we have a laptop, and what happens is that you raise your shock tester and then it free falls onto programmers. And these programmers on here or in this picture are nitrogen programmers, which will give you the trapezoidal waveform. But more importantly, they're programmable, which means that you could slowly step up your G levels until failure. So like I said, you start at a relatively low level, and eventually you stiffen up the programmers until you get the levels you want and the unit breaks. So this is just a picture for those of you not familiar with shock testing. Next slide is product improvements. So Herb actually just talked about this quite a bit, about when you put a little more money into a product to improve the product, for instance, just one extra screw, one extra bolt, one extra bracket, and to have dramatic increases in your just improvement of robustness. And when you improve your product, a few things happen, which is one, the reduction of materials. But reduction in materials, is good and everything, but it's more importantly that you have a reduction in package size. Because when you reduce the package size, you reduce the overall cube and you improve the overall density of your package. Because what we know about cushion systems and what we know about foam is just that most of it is void and lightweight material. And when you fit more units per pallet, it's easy to work with because of just easier resolution to fit packages into areas that they normally wouldn't be able to fit in. So this is just a brief slide about product improvements. And the last takeaway, or last point we want to drive home, is just the different packaging materials. So when you think about different packaging materials, they have different deflection properties. Deflection properties meaning its maximum percentage before becoming hard and pretty much just being same thing as no cushions or no foam in there. And the same amount of protection with different thicknesses, and usually with materials that deflect more are more costly because of good things in life cost money, and we all know that. But it might be worth it depending on the dimensional weight charges that you get, and more importantly, the cube of your palletization, which we'll go over some examples later. And here's just a picture from the lab that I just grabbed some foams that we used, or what our clients use, but On the bottom here, we have EPS, which is expanded polystyrene, and its deflection percentage is around 50%. On top of that, we have an EPS and an EPE copolymer, and that deflection is around 60%. On top of that, the grayish color, we have polyurethane. Polyurethane, it probably deflects the most out of all these cushions here at around 80%. So with 80%, if you have a 1-inch piece of foam, it could actually deflect 0.8 inches of that 1-inch foam, which is quite amazing. On top of that, you have EPE, which is expanded polyethylene. This is very, very popular in the electronics industry, and especially with an ESD coating. But with with EPE, you could probably deflect around 70% before hardening. And then finally, we have polypropylene, and polypropylene deflects around, I would say, like 75%.
These cushion materials are interesting in terms of their cost as well. And I'm no cost expert, but I'll give you some approximate numbers. If you have a certain volume of expanded polystyrene, and let's just put an arbitrary number on it, on that volume, let's say it's $1 worth of polystyrene, in equivalent volume with the expanded polystyrene and expanded polyethylene copolymer, that EPS and /EPE material, you're liable to spend $1.50 for an equivalent volume. You spend $1 for the EPS. Polyurethane, you're going to be in the $2 to $3 range for an equivalent volume of that. Again, depending on the materials. Sometimes they're pretty inexpensive. Sometimes they get very expensive. There are polyetherurethanes and polyester urethanes, and again, depending on your particular requirement, they can range from a double EPS to 4 or 5 times that. The polyethylene, the EPE expanded polyethylene, again, it depends on its density, obviously, and other factors, but it can be equal to or greater than the polyurethane pricing. And then finally, the so-called premium material in the industry for some applications is this polypropylene, or expanded polypropylene, because it's when you expand it, you simply put air into it by various means. But the propylene winds up being an extremely durable material. A lot of the automobile bumpers used to be made out of polypropylene. Some still are. So it's a very durable material, not too often used in packaging applications just because it's too expensive. But the EPS and the copolymers, polyurethane, especially the polyethylene foam, very common in packaging. But you can also get an idea of the costs, how they kind of follow that. They don't necessarily follow performance, and which is an interesting thing, and one that the package designers should be aware of. So let's go ahead and talk about the characteristics of each of these. Edmund?
Okay. Now that we've went through 3 pointers of 1, determining product fragility, secondly, of improving the product, and thirdly, of cushion materials, let's give you some formulas, calculations that you can take home with you. So this is just mainly a pen and paper exercise, and let's just say that this is the only data you have. And this being the only data you have, you could actually still calculate your cube, your dimensional weight, and you can still calculate how many units per pallet that you could fit per packaging configuration with this formula here. So this formula here states d min is equal to 2h divided by c times g, and finally multiplied again by 25.4. d min is equal to the minimum stopping distance or deflection for your cushion system. So this is just telling you how much cushion you need to add on each side of your product. H is equal to the design drop height of your package, and that's usually up to your own company, but you said, okay, theoretically, I want my package to always survive a 36-inch drop height, so you just declare H as 36. G is the fragility of your product, the determined fragility that you've known, and C is the percentage of cushion compression before bottoming out, or just the working percentage of your cushion before hardening. And here's just a note here that 25.4 is just to convert the units from millimeters to inches. So now that you have that example on your belt, let's do some comparisons here. So with this comparison, I have a table here, and one thing that I just want to point out on the table is that the design drop height will always stay the same as 36 inches because we want to make a apples-to-apples comparison as opposed to apples-to-oranges comparison. And what we're going to be alternating is, 1, product fragility. It starts at 50, and then we're going to 65, and then finally we're going to 90. And then for the cushion material, we're going to alternate between EPS and EPE. EPS with a cushion compression percentage of 50%, and EPE with a cushion compression percentage of 70%. So here's just some raw calculations, and I'm not going to go through every one of them, but I will go through the first case and the last case, which is, I would say, the biggest cube and the smallest cube. So with the first case, we have 50 Gs and packaging with EPS. And when you plug this into the equation, you get 2.9 inches of minimum thickness on each side. So because your product is 10 by 10 by 10, you add 2.9 on each side, and you end up with a 15.8 by 15.8 by 15.8 box. And for the last example here, we have a product fragility of 90 Gs. So you actually improved your product by 40 Gs here. And we're using you're using EPE, which deflects at 70% as opposed to 50%. And you have a minimum thickness of 1.4 inches on each side, which will result in a box of 12.8 by 12.8 by 12.8. So you look at it, 12.8 versus 15.8. You have 3 inches of difference here. So let's see if this 3 inches is actually enough to make a difference when you actually palletize these units.
It's important to note on this slide, there's a lot of numbers there, but basically what it says is that the product really doesn't know what kind of cushion is around it. It just knows shock. It just knows how much oomph, some impact, some numbers, some severity. And if with those given limits, the ones that are shown there, 50, 65, and 90 Gs, that there are different deflections necessary to achieve that. Okay, and again, the product doesn't know whether it's surrounded by styrene or urethane or ethafoam or God knows what all. It just knows shock. But those numbers that are given there are simply say that in order to slow down a product, if a product package system is dropping 30 inches, it hits the floor, in order to slow down at the rate where 50 Gs or less is transmitted to the product, then you have to have 2.9 inches of deflection. Well, this darn stuff only deflects 50% of its thickness before it turns into a brick. It bottoms out in the terminology of the trade. But you still need that 2.9 inches of total thickness on each side, and that winds up being the combination of the fragility of the product, the drop height, and the ability of the cushion to deflect. You put all those together and you get the numbers that Edmund is showing you there. Okay, I hope that's clear. Edmund, back to you.
Thanks, Herb. So since we've been talking about dimensional weight this whole seminar or this whole webinar here, let's just put these calculations through the dimensional weight for the common IATA and the common domestic to see if you shipped out these 6 packages, what you'll be charged with. So if you look at this table here, anything in red is when your package did not meet the minimum dimensional weight of the carriers. So with the biggest package of 15.8 by 15.8 by 15.8, and also the second biggest package of 14.4 by 14.4 by 14.4, you're definitely not hitting the minimums of 10.4 pounds per cubic foot and 8.9 pounds per cubic foot. So for these 2 cases here, you'll be charged minimum weight, which means that your charges will be adjusted. For the next box, which is the 14.1 cubed box, you're going to you won't hit the minimum weight for the common IATA, which is the air shipments, but you will hit the minimum weight for the common domestic. So with that, you'll be charged the actual weight. And then for the next 3 packages, which is the 13.2 cubed one and the 12.8 cubed one, you definitely hit the minimum weight, so you'll be charged the actual weights of 11.5 pounds per cubic foot or 12.5 pounds per cubic foot. So if you take these packages and you throw them on a pallet, just a standard GMA pallet, which has a footprint of 48 by 40 and a maximum stack height of 60 inches, and a maximum stack height of 60 inches, you get this spreadsheet here. And with this spreadsheet here, what you notice is that you get 2 clear divisions. The first 3 cases, you have only 18 units per pallet. And if you have 18 units per pallet and you want to ship out 1,000 units, you're going to need 56 pallets. Secondly is that for the next division, which is shown in green, you actually fit double the units per pallet, which is 36 units per pallet. And what you notice is that 36 is double 18, and what that means for the pallets is that you're halving 56 into 28. And when you think of that just in pure shipping costs, that just means that you have officially reduced your shipping costs by 50% by improving your cube by just a couple inches. So you look at these two cases here, 13.2 versus 14.1. That's just a mere difference of 0.9 inches on each side of the shipper, and that's enough to actually double your shipping units per pallet. And next here we have a slide that just, there's plenty of palletization softwares out there. For this example here, we just use TOPS here, and it's kind of sort of like a plug and chug. You would take your numbers and then you stick them in there, and then you have a pallet and you stick your dimensions in there and also your maximum stack height, and it'll spit out a diagram for you with how many pallets per shippers per pallet. And like I said, the first three cases we have 18 units per pallet, and then for the next three shippers we have 36 units per pallet. And what you notice from the left diagram to the right diagram is that it's doubled by just improving your package.
It's also important to remember that logistics costs are some of the highest. So just by optimizing a relatively small amount in the individual package, it is possible to have your distribution costs, and many, again, for engineered products, these are all the same here. Companies that make these kind of products have told us, and they have examples in the marketplace, so they're no secret. Electronic printers is a really good example. Just by shaving a few millimeters off the product, they're able to fit X number more in a given cube, and remember that it costs the same amount to ship a cubic volume by either air or not quite by air. There are some weight charges, but not many. But by truck or by sea or by rail, very rarely does the cost to the carrier change whether that container, that volume is full or empty. Okay, the cost differentials are very minor. So you, as a shipper of these products, can vastly improve the economics of the largest single identifiable cost in a delivered product. So don't ignore this. This is really an amazing source of savings if you're doing it now, or an amazing source of optimization of the product package system if you're designing this from scratch. And so FedEx is essentially doing us a favor, if you really want to look at it objectively, by forcing us to be more efficient in our overall design. Not just the package, although the package contributes, but the product and package together by getting the densities up to where they should be. Okay, back to you, Edmund.
Before we go on, it looks like we have a question from the audience, so I'm going to go ahead and give the floor to Greg.
Thanks, Edmund. I've got a question here from the audience. If you only stack to 60 inches, will you be charged the height of the truck, 90 or 108 and 8 inches, depending on the mode? Thus, the dimensional weight may still apply?
Let me see if I can answer that. This is Herb. Basically, if you're shipping what's referred to as LTL, less than truckload, you're not going to be charged for the complete cube unless you dedicate the truck. And if you dedicate the truck, that means nothing else goes on there but your stuff, and therefore it behooves you to maximize the density because you'll be charged for the entire truck, regardless of how much weight you have on there. So that's referred to as truckload shipments or rates. But if you're shipping LTL, that means the trucker puts your stuff and everyone else's stuff on there, so you're only going to be charged for the cube that you actually occupy, and you'll be charged a dimensional weight for that cube. And I think that's pretty much how FedEx is going to do it. It's up to them to cube out the trailer. It's up to you to maximize the cube that you actually give to them. So I hope that answered the question, but if there's anything further, shoot me an email and we'll try to clarify it some more if that's possible. Okay, Edmund, you want to continue here?
Okay, so it looks like we've reached the end of our presentation here, and we're going to close up with some conclusions. A couple points that we want to say is that, number one, knowing exactly how to calculate dimensional weight is key to minimizing adjusted costs and shipping the packages. So hopefully with our slides here, with our examples, you guys know at home now, know how to calculate dimensional weight of each unit or each product that you're shipping. And dimensional weight pricing is quickly becoming the industry standard. FedEx next year might be all other, shipping companies. The next year after that, you don't know. But it's probably best right now to start just preparing for dimensional weight across the board.
And across the board means every kind of mode, not just aircraft like it's been in the past, but ground shipment starting early next year. FedEx has already announced that. UPS will probably join them. They normally do. All the literature that I've read says that's exactly what's going to happen, and it'll be economics driving it. Remember, all this transportation is based on petroleum, and petroleum is not being made anymore. We're sucking out the last portions of it that we can get, for the most part, and so it's only going to get more expensive. That's it. The direction is very clear. So now is the time to start optimizing that whole process, because it's just going to get more and more and more expensive in the future. So again, I think FedEx is really doing us a favor by forcing us to really look at seriously the whole issue of density in shipment, or what they refer to as dimensional weight. Edmund?
Okay, and the 3 takeaways that we want to give people, once again, is that companies need to adapt in order to avoid adjusted costs. And the way that you could do that, and by the way, what I mean by you could do that, is that you actually have direct control over this, is number 1, determining product fragility, number 2, improving the product ruggedness, and 3, changing or just evaluating cushioning materials to see what different cubes you get. And let me just elaborate on the first 2 points of determining product fragility and improving the product. So far too often do we see just the package just being a byproduct of the product. And what this means is that the product and the package, they run in series and not in parallel. And when the product development is done, they give the product to the packaging engineer and say, okay, packaging engineer, okay, supplier, give me a package that protects this product. It fails at 40 Gs. And as a packaging engineer, you have no say in it, or if you do have a say in it, it's really, really difficult for you to make any changes, because the product's ready to launch and you have no time anyways. And what that means is that the package is a byproduct of everything, and what that also means is that the cube is a byproduct of everything, and your package is just like, okay, you calculate to have 4 inches on each side, and we can't really do anything at this point because it's already too late. So the quicker that you could implement the package in the product and work together hand in hand, is you'll have a more effective, more efficient system, more efficient and effective cube and dimensional weight ratio. And I think that is it, but Herb probably wants to chime in a little, so I'll give the floor to him.
Okay. I think that pretty well wraps it up. Again, with a 1 hour approximately webinar, we can only scratch the surface here. But the important thing is awareness, that you are aware that, number 1, that this dimensional weight shipping routine, the method of calculating cost, is at your doorstep. Some of you will be affected by it grossly, some only a little bit. We'll all be affected to some extent, because it'll shift cost in distribution, and distribution winds up being a huge cost for everything that we do. And the second thing I want to specify is that there are some things you can do about it. It's not like you can just roll over and play dead and watch it go by. There are things you can do about it. We attacked a few of those things in our presentation here. There's probably a lot more that we didn't attack. Those products that are not cushioned, for example, we didn't spend a lot of time on those. And there's a lot of things you can do. So if there are any questions on this, we stand ready to help you in whatever we can. And that's the whole purpose of the webinar. We're here to be a resource for those who have to ship. So from this point on, if you're concerned about that, if you get leveled by it, if your shipping manager has a heart attack, well, call 911. But shortly thereafter, call us and we can help you with it. Okay? But thank you for attending our webinar. Thank you to Edmund and to Greg for doing the bulk of the heavy lifting here. And I hope you have a good time in the future with this whole process. And Westpak can help out. Please let us know. Thank you.